Okay, well, I guess we'll go ahead and get started. This is the lab session where we'll cover the homework problems from the sort of time to event meta-analysis. Okay, so we're going to cover the combining of Kaplan-Meier curves in the two different approaches that we looked at last time. As usual, if you have any questions along the way, feel free to post them to the questions box, and I'll be checking there periodically to see if there's anything I can answer. So recall we had two different approaches. One was to combine the observed survival probabilities directly using some information that we have about the correlated nature of those outcomes. And the second approach was to model independent binomial events that are the numbers of events happening in non-overlapping time intervals over the course of a study. And so the first example that we worked on was using some data that was published in a paper by Deer that had these 17 randomized controlled trials to test the effect of adding chemotherapy to radiotherapy in postoperative malignant glioma. And this was the data where we were able to see that the red lines here were the chemo plus radiotherapy treatment arms, and the blue dots were the radiotherapy treatment arms alone. And there seemed to be some modest benefit, at least in some studies, of adding chemotherapy to radiotherapy, but it wasn't clear how large that benefit is. And so we began in the course of the lecture by fitting an exponential survival time model and using a logit transformation, and that gave us the sort of variance covariance matrix that had structure or that had elements that had this sort of form to them, where the variance or covariance depended on the standard error that was observed for the survival curve plus a function of the survival probabilities themselves at the two time points that we're calculating the covariance. We use non-informative priors for the main effect parameters and the between study effects. And we had some WinBUGS code. And we saw that when we fit that model, the exponential, when we fit that model to the data, the exponential model really wasn't a great fit, and it seemed like some additional modeling would be necessary. And that was essentially the homework for this part of the homework exercise, was to fit up a model that allowed for some additional curvature. And that could be a Weibull model, a Gumpert's model, or a log normal model. All of those allow some additional curvature at the beginning and at the end of that survival function. And then I said, if you had time, you might also want to compare the results to a model that doesn't account for any correlation, and just to see what kind of differences in the inference you might have. So what I'll do in the first half of our lab session today is just step through fitting one or two of those models to give you a sense for how we might modify the code and make some comparisons with the inference. So first, what I'll do is I will set my working directory here to the package or to the area where I have my data. And for me, that's on my E drive, 260 USB, MI260. And then we have it in survival examples. And I put that in here. Survival examples. I think I have these answers here. Let me jump here. So we have MI260, survival examples, survival homework answers. Okay. Okay. Oops. Got to get my quotes lined up there, right, huh? Okay, so now we've got our data set up, and we'll read in the data set. We'll set up our, load our libraries that we'll be using. Read in the data, create a time variable. All of these we stepped through it last week during our lecture, and hopefully you had a chance to check through the code. This set of code, again, just extracts the standard errors and the survival times, converts them from a percentage scale to a probability scale by dividing by 100. And then this bit of code was really the kind of a little bit of the workhorse here in R to come up with those precision matrices that we're going to be passing into the model. So the next little bit of code here was just to set up some functions that'll be useful, and then define some data and initial values. Now, all of these were for fitting the exponential model, but we'll see that when we get to the survival model, or the WinBUGS model, that there's really very little difference. So in fact, let's look at that. We'll open up the exponential model and the WinBUGS model, and we'll compare the two. Oops, that's right. It doesn't give us a very good view of the files themselves. So let's look at the file here. Here's our exponential model, and here's our WinBUGS model. So remember, with the code for our exponential model, we had our input data was a matrix, and what we passed in was already the logit transformed survival values, and each row corresponded to a treatment arm, and there were 4 columns because we had 4 time points, or up to 4 time points in each study. And the model said that that 4 vector of observed time points for over a treatment arm followed a multivariate normal distribution. It has some mean vector on the transformed or on the logit scale, and then a precision matrix, which we know we have defined based on the theory and the approximation to what that covariance matrix should look like. And for the exponential model, we had that our transformed mean response was just the logit of a model-based prediction, which we called mu. And that mu is our exponential survival time model. It was just e to the minus lambda times time. And here we're standardizing time to be so that our lambda had a interpretation of the rate per year, because time in this particular example is set up in months. So when we're switching from a exponential model to a WinBUGS model or to a log normal model, all that we really need to be changing here is this code here that defines that mean function, because the variance covariance matrix or the precision matrix is defined simply in terms of the observed surviving proportions and the observed standard errors. So that really, this part here is really data that's coming in and isn't affected by what model we're using for the mean. So if we were to compare the code for fitting the exponential model here on the left with the WinBUGS model on the right, we'd see the only difference I have here is this line here. And for fitting the WinBUGS model takes the form e to the minus lambda times time raised to a power. Some formulations you'll see will include this lambda inside this we'll also be raising lambda to the same power. In this case, I've left it out. Gives you a slightly different interpretation depending on whether you put it in or out, but the model fits are the same. And so here we're raising that time to a power of gamma, and we're letting gamma vary from trial to trial. So in addition to so that's the only change to the part of the likelihood part of the model. We also have, or the model for the observed outcomes, I should say. We also need to define a model for the gammas. And here I just assumed that the log of the gammas followed a normal distribution between studies. And the overall gamma value, or the overall mean gamma value, is mu dot gamma, which really perhaps should be mu dot log gamma. And the between study precision of those log gammas is prec dot gamma. And then I put a uniform prior on the between study standard deviation, which I've labeled here as omega dot gamma. And that uniform prior goes from 0 to 2. So you could consider different prior distributions, maybe a different between study distribution for the gammas. You could even use a gamma distribution if you wanted to. But the key piece here that I want you to take away is that as we move from an exponential model to a Weibull model, the main piece that you're changing is just this chunk of the code right here. Okay, so if we go ahead and run that, we'll set up our initial values for the Weibull model and tell BUGS which parameters, or tell R what parameters we want to monitor. And then we'll go ahead and fit this model in the WinBUGS. And it runs fairly quickly. I'm going to leave the debug option here set to true. So rather than making some diagnostic plots in R, we'll just take a quick look at the diagnostic plots that BUGS gives us, just to get some comfort that the model's converged and that we have our MCMC sampling is working well. Whoops. There we go. While that's running, I'll just check and see if anyone has any questions. So you'll see when we move to fitting the log normal model, maybe I can open that here while BUGS is running. Again, all that's going to change is essentially this line here, this line of code here. So the log normal model would say that our survival times, the log of the survival times, would follow a normal distribution with some mean and variance or standard deviation. And the mean on the log scale will essentially determine where the median is on the observed on the non-log scale, on the raw time scale. And the standard deviation of that log normal will depend on will tell us how curved that, or how steep that survival function drops off. If you have a very small standard deviation of the log normal scale, you get a very steep survival curve. And if you have the bigger the standard deviation gets, the sort of the less steep the survival curve becomes. Okay, let's see how. Looks like we ran into a problem here with WinBUGS doing its updating. I'm not sure what caused that. Well, it ran fine before. Let's try giving it another go here. Maybe a different set of starting in it, or a different set of initial values. So it seems like it's getting through the first 10,000 okay, and then maybe it seems like the problem came when it was trying to do some additional sampling from the Markov chain. We'll come back here to our log normal example, just to look at the code while BUGS is running for now. So in the way that I formulated this for the log normal model, which is here. So the BUGS has a function called phi, which provides for us the standard normal cumulative distribution function. And if you remember your Statistics 101 class, the survival function is just 1 minus the cumulative distribution function. So if we were to say that a time to event variable follows a log normal distribution. Then the survival function should be 1 minus the cumulative distribution function for a normal distribution. Because BUGS provides us the standard normal cumulative distribution function, what we need to do is center our observed times on the mean, which I'll denote here by lambda, and divide through by the standard deviation, which I'll denote here by gamma. So I'm using the same parameter names as I used in the Weibull model, but they're serving slightly different purposes here. So lambda here is the mean for the ith treatment arm, and the mean log survival time for the ith treatment arm, and gamma is the mean between the mean. Sorry, gamma is the standard deviation of the survival times in the ith study. So we'll come back and run that model as soon as our Weibull model is finished. I'm guessing that it's wrapping things up here. Okay. So here are our history plots from for the parameters that I monitored. I essentially monitored all of the individual treatment arm level parameters or study level parameters, as well as the overall mean parameters and the between study variances. And so as we look at our trace plots, we want these to look like those hairy caterpillars. So we're seeing that the chains are all sampling in the same space. Means that we've run our model to a good burn-in because these are essentially horizontal. They're not showing any clear trends over time. If that was the case, then we would think that we hadn't quite gotten to that steady state place where we need to be to sample from the posterior. So we can see all of these history plots look pretty good. And I won't scroll through them all, but I'll send you the code and you can get these and look at them at your own leisure. But we're going to look here quickly at our posterior parameters. We have a mu delta, which is the difference in the event rates. And here that is estimated to be about minus 0.5 for the posterior median. The posterior credible interval that's going, let me just make sure I'm looking at the right columns here. No, I wasn't. So we have the posterior median posterior median difference in the event rates to be about minus 0.3, with a credible interval going from about minus 0.46 to minus 0.16. And so we can use similar kinds of plots that we had used in the looking at the exponential model. So for example, I could make this a plot of the observed data and the model estimated fits. And I see I haven't defined something here, OSM. And that OSM is just a subset of the data that we have. Maybe I have the wrong names here. Head of DM is endpoint. DM $n. Okay. So that'll be our OSM, and now we can plot that model fit. And we'll see that the Weibull model gives us a reasonably good fit. I forgot that I had to convert these back to probabilities. So let's make that plot again. The Weibull model gives us a reasonably good fit. We can see that some studies here have more curvature, like study 10, than others, like study 9. And so the Weibull model clearly is giving us a better fit than than the exponential model. And if we were to look at what that gamma parameter is, let's look at our fit3 $ sims.list. Let's just look at what parameters we have there. So the parameter of interest here will be mu gamma. This is that shape parameter, but on the log scale. And if we look at the posterior summary of that, we'll see that the posterior median is around 0.2. And if we look at maybe the quantiles of that, or actually we'll just plot a density plot of that to give us a sense for how much of that mass is above 0, which correspond to a shape parameter of 1, which would be the exponential distribution. And so here we see that the vast majority of the density here is above 1, so it's giving us some indication that above 0, which is giving us an indication that this shape parameter is really different from 1. And if we wanted to really see that on the non-log scale, on the raw scale, this is our estimated shape parameter here is around 1.2. That would be the between study mean. Okay, so it would seem like we talked quickly through the log normal model. I'll just go ahead and fit that model for you to give you a sense for how that model fits. And it turns out that the log normal model provides a slightly better fit to the data than does the Weibull model. And so we'll fit this log normal model using the correlation structure that the theory tells us should be. And then what we'll do is I'll compare that to fitting a log normal model where we're getting a similar kind of trap here. We'll compare that to a log normal model where we assume independence and compare and contrast, particularly the estimate of the drug effect on that rate parameter. This is interesting. So we're getting slightly different behavior here when I run it through Windows and when I ran it on my machine previously on a Mac. Let's try and do it this way. Oh, I'm not going to do it that way. Let's use slightly different log starting values here. So we have omega delta starting gamma off at 0. Start that off with something that's a little bit closer to centered somewhere, and we'll start the difference off, give us a slightly different set of starting values for our Markov chains. We'll start the deltas off assuming there's a little bit of an effect, and we'll start the gammas off assuming there's a little bit of shape different from, or a little bit of additional between, sort of a little bit more curvature than you would expect if that standard deviation was 1. So I'll check and see if anyone has any questions quickly while this is running. It looks like we have a little bit better performance here with these. Whoop, no we don't. All right, well, Technical difficulties. um, so we have one question here. What criteria besides visual are you using to select models? That's a good question. Um, what I'm showing you here is essentially visual. Really, if you want a more numeric criteria, the one that's typically used is the deviance information criteria, the DIC. If you've taken any of the other BUGS courses, either through Metrum Institute or through other places, you probably would have come across DIC. You can think of, if you haven't, you can think of DIC as a measure of an information criteria, not unlike Akaiki's information criteria or AIC. Um, the idea is it's a measure of model fit that penalizes you for the number of parameters. So there's some attempt to come up with, to push the model fit towards a model that is parsimonious. Because in sort of classical model fitting, the more parameters you throw into a model, the better fit you're going to get, even if the parameters aren't particularly useful in making inference. So DIC is in some sense a Bayesian. It's a Bayesian cousin of AIC. You can get DIC out of WinBUGS, and or you can calculate it yourself using output from DIC. Do you need to have nested for DIC? I think there's a debate about whether you need nested models for DIC or whether you can just use DIC as comparisons across non-nested models. Typically, if you're thinking about it as coming out of likelihood-based inference and using the likelihood and thinking of AIC as sort of something akin to a likelihood ratio test, and certainly in that context, the likelihood ratio test needs to have nested models. AIC itself, and in fact DIC, I don't think really relies on that strictly speaking. So I don't think the models have to be nested, but I don't think that there's a complete consensus on that point. Really, what DIC is measuring is it's a measure of the kind of average deviance or average log likelihood plus a penalty term, which is related to kind of an effective number of parameters, and that effective number of parameters is itself related to the deviance. So really, you're kind of comparing how well does your model fit, penalizing you for a number of parameters, and that we're not making a sort of a quantitative, there's no test statistic to compare two models, whether they're nested or not. So we're not relying on nesting models in the sense that you'd need to for like a likelihood ratio test. I'm not sure what's happening here with this particular model. This model had been running fine previously, but let's. I think for the sake of time, what I'll do is I'll post this code for you all to use at your leisure. And if for some reason you're finding that it's not running in your system as well, we'll try and debug further. What I want to do though is make sure we get into the second set of homework problems. So I think what I'll do is I'll switch gears and move over to that right now, or unless, well, maybe I'll post it to you, to everyone here. Will you? We can either work on sort of debugging this a little bit to try to delve into what some of the issues might be with this code and make the comparisons here, or we can move on to the second piece. If anyone has any strong feelings one way or the other, let me know. Okay, not seeing any. I think we'll shift gears. We'll come back to this at the end when if we have some time. So for the second homework problem, what we had was, if we come back to the homework, to the example, we had these multiple myeloma data from 6 studies, where we're modeling overall survival and comparing two treatments in the course notes, and then as the homework we're asking you to compare actually the 3 treatments that were available in the data set. The idea was to refit the model, including data from this 6th study that compared CTDA to MP, and then explore whether or not you feel like you needed some additional model or model with additional curvature to give a better fit to the data. And so the answers are here in this myeloma survival answers. Our code, and we'll post that to the website at the end of the lab session today. So let's go ahead and remove all of the objects we created previously. And then we'll read in the data and set up our code here. So really for the first bit of homework, there's really nothing. You were able to take the code that I provided, make some minor modifications to it. Whoops. This plot here is not right. Oh, I see. Okay. So what I've done here is I've read in the data. By default, what R will do is sort the factors. In this case, the factor that we're interested in is treatment group by alphabetically. And so what we need to do in order to make, I think, nicer plots is we'll set MP to be the reference treatment group. And so there's a relevel function here that allows us to do that, set the reference group. And then we'll go ahead and plot that using similar colors as to what we had before, but now we'll use green to denote the CTDA group. And here's that 6th study, the MRC9 study that compared MP to CTDA, and we can see in this particular study there's really no difference between those 2 treatment arms. So the homework problem asked us to fit the expand the original exponential survival model to include these 3 drugs. And so if you recall, the code we had before said that we have this variable R that follows a binomial distribution. R is the number of deaths in these distinct time intervals. P is the probability of a patient dying in that interval, and N is the number of patients at risk over that interval. And here our model says that, or just by basic laws of probability, the probability of dying in that interval is the probability of being alive at the beginning of that interval minus the probability of being alive at the end of the interval divided by the probability of being alive at the start of the interval. And our model for S here is this exponential sort of survival model, where we put allow different rate constants for different treatment groups. And so by incorporating this 3rd treatment arm, what we needed to do was just simply modify our model for lambda. And here, the way that we've done that is to have a variable delta MPT, which describes the difference between the MPT group and the MP group. And that's because we know that we'll pass in a numeric variable called group, and if it's equal to 3, that's denoting that the treatment arm was the MPT group. And if that variable is equal to 2, that will correspond to the CTDA group. And so we'll have a separate parameter that is the difference between CTDA and MP in the log hazard. Then we need to put a prior on this delta CTDA. And here what I've done is I've assumed a hierarchical model for the delta CTDA. So there's some between study variability, even though we only have one study that has CTDA. And in order to obtain an estimate of that, I'm just making an assumption here that the between study variance of the effective MPT and the effective CTDA above and beyond MP, the between study variance is the same between CTDA studies and MPT studies. And in doing that, I'm able to estimate this between study variance of CTDA, and then use this hierarchical structure, this multi-level structure for the effective CTDA, even though we only have one CTDA study. Alternatively, we could have just estimated this a single parameter here and said, given that one study, that's the effect, our best estimate of that, of the overall CTDA effect. Okay, so we can go ahead and run this model. We'll set up the data and the initial values and the parameters that we want to monitor, and then go ahead and run this. While that's running, I'll check and see if there are any questions. Okay, well, I'm glad we're headed in the right direction to working on the second piece. So for the second piece, really the model code itself, and the way we haven't changed the fundamental model. All that we've changed is by incorporating the way to incorporate an additional treatment arm. You can imagine if you had other covariates like continuous covariates or other sort of baseline covariates, you could include them in the same way here in this exponential sort of framework. And then what we'll do next is look at how to modify that code to fit a Weibull model. Again, here I've set the debug option to true, so we can just look at our MCMC diagnostics in WinBUGS itself. And you can see again that we have our chains have converged reasonably well. We're getting good mixing of the chains. Some of these chains are getting fairly large values. So here, for example, the delta MPT from study 6, we're seeing some values around, -10 and as much as maybe 5. So remember, that's on the log scale. So those are pretty corresponding to some pretty small and big values, respectively. And part of that is because of the prior distribution we've used and the fact that we only have 6 studies. So with only 6 studies, we're not able to get much information about the between study variance pieces, and so the prior is playing an important role there. But if we do look here at our overall mu lambda, here was the log hazard in the MP group. Mu delta p was the overall between study mean effect of the of MPT relative to MP. We have a credible interval here, a 95% credible interval that runs from about -0.57 to about 0.2. And for the mu delta CTDA parameter was the parameter, again, that was the overall mean effect of CTDA relative to MP. Here we have quite a bit less information. That it's centered around 0, with a credible interval ranging from about -0.8 to +0.85. So Not as much information about CTDA on average as we have about NPT, and that makes sense because we have only 5 studies of NPT and 1 study of CTDA. Our between study variance of the drug effect, which is this omega delta, is coming in at a median of 0.25 and a credible interval of 0.04 to 1.01. I didn't ask to monitor it here. We could have, but this is our this is where BUGS is providing us the DIC, and in fact, if we through R to WinBUGS, we can ask that it pulls this back, and we could compare here our DIC of 923 for this model with the DIC from an exponential model, for example. And just to give you a sense here, this this D bar is the average deviance, so it's averaging over the parameters for each treatment arm, and sort of the the uncertainty in those. So this is the posterior mean of the deviance. D hat is the deviance evaluated at the posterior mean of the parameters. And you can use those two things to get this PD, which is the in this DIC formulation is the effective number of parameters in the model. So we have 6 deltas, we have 6 delta CTDAs, we have 6 delta MPTs, we have 6 lambdas, we have some variance parameters. So we have quite a bit more, large number of parameters, but the effective number of parameters here is about 10. So if you're not familiar with DIC, you can there's some help for that in the WinBUGS manual, and if it's of interest, we can maybe do a little segment here on DIC. So we've got our fit back here. Let's look at how that model, what some model predictions from this model look like compared to the data. It turns out I should have. Well, we'll make the plot. We'll fit this model first. We'll plot the model fits first. So what we're plotting here is a similar kind of plot to the one that we had in the notes previously, where we're overlaying some 90% credible intervals, shaded regions over the model fits in the data. Not surprisingly, here in this study that has CTDA, because there was a large amount of uncertainty about the effect of CTDA, the credible interval around the predicted survival curve is fairly large. If we wanted to now consider fitting a Weibull model instead of this exponential model, all that we're changing is those 2 lines of code that relate to the model predictions itself. So let's look at that, and that's in this myeloma model 3 drugs Weibull. So again, the code is very similar to the exponential model. What's substantively changing is in these 2 lines of code here. This says, remember, this was the part of the code that defines the survival function at the start of the time interval, the survival function at the end of the time interval. Because we're using a Weibull model, we define the form of the Weibull survival function here. So as before is e to the minus, and in this particular formulation, I put the lambda inside the parentheses. So this is like e to the minus lambda times time raised to the gamma power. And again, we're letting, in this formulation, letting gamma vary between studies. And in that I put in that hierarchical formulation of the model, we're saying that the log of the gammas follows a normal distribution with some between study mean, that's mu.log gamma, and between study precision of prec.log gamma. And then put uniform prior distribution here on the between study standard deviation of those gammas. And as before, made this assumption that the between study variance of the deltas is the same. sort of the delta MPTs and the delta CTDAs. Okay, well, let's go ahead and run that. Hopefully we'll have slightly better luck with this model than we had with the other one when we were working with the glioma data. Well, that's running. I'll check and see if we have any questions. There are none yet. It's going to turn out that with this model, the WIPO model is really not any improvement over the exponential model. And I apologize. I should have monitored DIC here. Let me show you how you can do that. Actually, it looks like I think I might have monitored DIC. Yeah, in fact, we will get that. By default, R to WinBUGS will monitor the deviance and will bring back a DIC. You can see here, it's set the deviance as a node to monitor in bugs, and it's set the DIC. So what'll happen is we'll get that returned back to us, and then we can, for this particular example, we can do a comparison of the DICs. All right. Bugs is still chugging away here. This model is taking a little bit longer to fit than the exponential model, not surprisingly. Okay, so now it's finished. It's going to give us a little bit of some of those diagnostic plots. I'll just, due to the sake of time, I'll skip these. You can I'll just scan through them quickly. So you can be convinced that we have attained convergence of our Markov chains, or at least you can see that there's no obvious divergence in the Markov chains. I've created this object called fit.wibble. And let's look, when we bring back our R to WinBUGS object, we have an element of that called DIC. So if we look at fit.wibble, DIC, for the Weibull model, we have a DIC of 92.8, and I can't remember what we call that other model, fit1. Fit1. So if we look at the DIC of fit1, that was our exponential model. Here our DIC for that model was 923.1. So by adding in that shape parameter and some between study variability in that shape parameter, we dropped our DIC by about 0.3. That's a minimal decrease in DIC and would lead you to believe that the simpler model, the exponential model, is just as good at making predictions at that individual treatment arm or observation level as the Weibull model is. And in fact, if we look at a summary of our of the parameters in our model, we have I monitor these gammas. We can see that the posterior mean, or posterior median rather, for most of the gammas is very close to 1. There's some around 0.9 and some around 1.1, but there's very little deviance, no clear deviance from 1, which would be, where 1 is our exponential model. And if we look at the posterior distribution for the mean of the log gammas, well, to 1 decimal place, these are, the credible interval goes from -0.1 to 0.1. That's giving us some indication that we have that our posterior distribution for the overall average gamma is very close to 1, indicating an exponential model. Again, that's backed up by a comparison of DICs. And if we were to plot the model fits from this, plot the model fits from our Weibull model, we would see fits that look like this. We could look at the, and after we pull up these model fits, we'll look at a density plot for gamma, just to, again, one more visual check to see what kind of information we have about that shape parameter. So here we see, again, I'm not overlaying the two plots, but if you were to look at the exponential fits and the Weibull fits side by side, you'd see that there's very little difference. And in fact, if we wanted to look at a density plot of our mu.log gamma, in fact, we'll go ahead and exponentiate that to put that on what our posterior distribution for gamma is, or for the between study average gamma. It looks like this, and if we throw a line on there at 1, you see that we're quite confident that gamma is lying here between something like 1.8 and 0.8 and 1.2. And you could obviously do some more quantitative summary than using functions in R. So those were the 2 bits of homework that I'd asked you to take a look at. We have, for this example, refit the model, including the data from the CTDA study. I haven't done any real quantitative comparisons or model-based predictions using the model, but if that's of interest, we can either cover that in a follow-on lab session, or you can figure that out, work on that on your own, and post questions back to us through the website. And you can either let me know now through the questions panel, or think about it and post to the discussion boards later this week. And subsequent to that, then we've looked at trying to do some model selection here between an exponential model and, in this case, a Weibull model. Okay, I guess that really brings us to the end. We can go back in the last couple minutes we have and look at the. Well, I think I'll leave that to you. You can work on the log normal model. I'll post that code for you to use right now after we finish the session, and then you can, if you have problems running the code for the glioma data, post questions to the discussion board, and if I'll work on debugging that. And if I figure out what the problem was, I'll certainly repost some new code. Because strangely, it was working earlier. I'm not sure what's going on right now. So I'll hang on here to see if there are any final questions, and if not, then we'll reconvene on Monday for our next lecture. Okay, well, I don't see any questions coming in, so thanks to everybody for the lab session, and as usual, if you have any questions, post them through the discussion threads. Thanks, and we'll talk to you next Wednesday.